start with Tahboub. She's going to talk about how to architect a query compiler, which is a follow-up work on like something that was published, what, 3 years ago? And that received a lot of attention, so I think I'm really excited to hear what she has to say.
Thank you, Holger, for the introduction. Good afternoon, everybody. In my presentation today, I will talk about our work in which we revisit how to architect a query compiler. This work is co-authored with Grigory Issertel and T.R. Krampf. Interpreting queries without any kind of code generation was a sensible choice for many decades because evaluation was dominated by I/O. But ever since query engines moved to main memory, I/O cost got eliminated and workloads have become CPU bound. And there has been an ongoing debate in the research community about what's the best way to architect query compilers. And this is perceived as a difficult task that requires skills and techniques that are fundamentally different than the interpretive evaluation, which a typical database developer is very good at. We joined this ongoing debate, and we aim to contribute by showing that building a query compiler can be as simple as writing a query interpreter in a high-level language. A traditional query engine works almost like a query compiler, but it misses the last code generation step. So the key architectural question is how to get from a physical plan to executable code. First, we look at Hyper, a pioneering query compiler developed by Thomas Neumann's group in TUM. Hyper uses a programmatic LLVM API to generate a query code, and it has excellent performance, but at the expense of low-level implementation that spreads across the query engine. Another recent system called DBLab, developed by Christopher Koch group in EPFL, and recently published in Sigmod 16, DBLab is a high-level query compiler that is written in Scala and generates optimized C. In order to do so, it goes through a number of intermediate languages and explicit compiler passes that are necessary for optimal performance. So in both instances, there is a significant development effort than writing a simple query interpreter, which is the common skill level of a typical database developer. So our goal in this work is to be able to develop a query compiler in a high-level language that achieves the performance of the low-level approach without having to go through intermediate languages or explicit compiler passes. And we developed a query compiler that is called LLVM, which is a single-pass high-level query compiler implemented with guidance from the first Futamura projection that I'm going to talk about next. A glimpse about its performance, it's comparable to Hyper in TPCH, and when we implement the same non-compliant optimization from DBLab, LB2 outperforms DBLab in most of the TPCH queries. So, Cod, in the 1970s, published his work about relational model, and the key insight was data could be profitably represented as a high-level relation without explicit reference to a given storage or traversal strategy. And as we all know, Cod's work had high impact and resulted in a multi-billion industry. And to a large extent, it owes its success due to the automatic query optimization that works very well because of the narrow semantics of the relational algebra. Around the same time, Futamura published his work on partial evaluation, where the key insight was compilers are not fundamentally different than interpreters, and compilation can be profitably understood as the specialization of an interpreter without explicit reference to hardware or code generation. Futamura's work was well perceived in academic circles, but it didn't have the same success of Code's work, maybe not yet, because automatic partial evaluation turned to be a hard problem due to binding time separation. But as they say, all is not lost. And at least in the context of data management, maybe there is a practical solution with help from the programmer that allow us to realize the first Futamura projection and obtain a compiler from the query engine or the query interpreter with help from the programmer. So I'll try to explain what is Futamura projection in this context for those who just heard about it. So A is the typical query engine that processes SQL query and dynamic input. So the first Futamura projection says that if there is, or if there was, automatic partial evaluator called Mix that can process SQL engine and SQL query, then it gets the target. But it's not possible to implement this partial evaluation. So we need a practical way with help from the user to stage the query interpreter and tell us which parts should be specialized and which parts should we visualize to get to the first Futamura projection, which is the basis of this work. So what is programmatic specialization in high level, or how can we realize it? So in the most generic sense, if we take a function and instantiate it with a given argument and simplify. So here's the power function with x and n. If we know the value of n, so we can have a specialized version that gives us this residual code. And how this can be realized, one way is to create a symbolic data type and then overload the multiplication and let it emit the desired computation as a side effect when power is called. So if we can implement an interpreter such that it evaluates a query input on symbolic data type, which is the records, yeah, we can get this achieved. So while we can do this using the MyInteger style, but it pays off to use a generative programming compiler like the lightweight modular staging for code generation and low-level plumbing. And the way LMS is used, it uses a constructor called rep that denotes this is the future stage. So x is rep of integer. In the previous example, it was MyInteger, and it realizes, it emits the code on the right. So just while we are at it, we notice that the shape of the specialized code follows the shape of the interpreter because we evaluate the interpreter that emits something as a side effect. So just, well, it's a nice thing that we can control the shape of the emitted code by engineering the interpreter in a particular way. So the Futamura projection is a result, it's something conceptual. So we need to be able to realize it in our query engine context. So first we try to specialize the volcano evaluation, but it turned out that it's not efficient due to the control flow dependency. And here's a quick example. Okay, this is a meaningful query, but I'm only interested in the select predicate, which is rank less than 10. And to remind you that the volcano operator calls next, and next, the record is returned can be null. So the operator implementation should check for the null. And this null cannot be specialized, so that's why it doesn't produce an efficient code if we are to specialize the volcano evaluation. So what about the data-centric model? So the data-centric model is a push-based. So the consume, so it has two methods, produce and consume. Produce get the record and consume carry the operation. So it's designed so that the consume is only called on valid data, so we don't have the previous problem. And hence, specialization can fully remove the dispatch on the operator structure. So after spending some time working on specializing the data-centric model, one of the things that are not comfortable is the evaluation is spread across the produce and consume. So there's kind of this conflation in phases, or you have like mental effort of keeping a track of which operator called the consume. And here is like a quick example. So this join will call a produce on the right, on the left, which will call the produce of the select, which will call the produce of the scan. Then the scan will call the consume of the select, and the select will call the consume of the join, and we'll get the tuple. So as a first contribution, we decided to refactor the produce and consume into a single method with a callback, so we don't have to worry about this mental tracing of the states of consume. So now we get to this question is, where in the query engine we should place the code generation. So if you remember my power example, there was a print function that emitted some code. So where this should be placed in the query engine to get the code generated. So a simple way is to do operator level and specialize each operator as a string with a placeholder for parameters, but like this is really bad idea because just then you can generate code, but this code is not going to be optimized. And the literature talk a lot about it. So a second idea is to push specialization into the structure that makes up the query engine, which is the record and the hash map. And it will avoid some of the earlier problems, but again, we will get a generated code with some high-level things like a new record, a new hash map, and these things are not optimized yet. This is, for example, in our case, this is a Scala, and we want to generate C, so if we are to use libraries like glib, we will get with inefficient code. So, like on a high level, what we're doing in LB2, we specialize the internal data structures, and we introduce some abstractions. We call it compile time abstractions that help us to implement all of our data structure as we're writing a normal query engine, but these are internally call the code generation. So it pushes the code generation into the level of the primitives like my integer type. And LB2 internally uses LMS. And this has the same effort of writing a query interpreter in a high-level language. And we did some experiment. We evaluated we compared with Hyper and compared with DBLab. So LB2 is is comparable to Hyper, and it outperforms DBLab, and just why exactly it's discussed in the paper, so there's a couple of minutes. And also, we implemented the same optimizations from the DBLab paper, and we were able to outperform DBLab in most of the queries. Some queries, DBLab still outperformed LB2. And since DBLab does so many compiler passes, so it's natural that the loading time is higher in their case. In parallelism, we compared with Hyper. So it was comparable. Some queries, they did better. Some queries, we did better. In the code generation and compilation, we compared with DBLab because Hyper is not, like the version that we have, it doesn't give us this information that we needed, and it's no longer public, so we compared with DBLab. It was comparable except for some queries where they did more compiler passes. And as a productivity, we were able to implement the same optimizations with less lines of codes, but we have to mention that DBLab uses a system compiler, which is 30K lines, and LB2 is using 2K out of the 7K. So what we want to discuss is like a few more things. So there is a confusion when we read in the literature between what is a template expansion and what is a single compiler pass. So template expansion is a first-order context-free template, or have so many problems. But it's not single compiler pass. It's single compiler pass like LB2 can perform context-dependent optimizations. So the questions that naturally we ask is, so are multiple passes necessary? So multiple passes help if one step of expansion or specialization exposes information to an analysis that is not present in the source. But for the SQL case, the optimized query plan contains all the bits are needed. So additional abstraction levels between the operator and C code may not provide tangible benefits. So when to use multiple intermediate languages, one case is when we have multiple front ends. So we have SQL, ML, linear algebra, that multiple DSL. So each DSL can be optimized on its own. Then multiple compiler passes are needed to translate all these DSLs into a common core and do some optimizations. Thank you very much.
Right. Do we have any questions? There's a mic. Okay, I'll kickstart one. So I'm curious. There is some recent work, like in the functional programming community, basically talking about, like, how some things in push versus pull-driven query execution are just harder to do in one or the other. The example I think they use is sort-merge joins are hard to implement in a push-driven query compilation system. And so now my question is, through your specialization, are you making this worse? Can you support, like, do you have an idea how you can support sort-merge joins or any kind of, like, push-up, pull-driven, naturally pull-driven algorithms?
I'm not sure I understand your question.
The question is, like, in a push-driven system, it is incredibly hard to implement sort-merge joins, virtually impossible. And so there is this argument of saying you need a pull-driven engine if you want to implement that specific algorithm. And there are other examples. So are you preventing us from implementing certain algorithms by basically?
So here we're not saying that so what we're presenting here is a way of generating code, regardless of if it's what's the evaluation model. Like, we can implement whichever algorithm or whichever evaluation that we want. So what we're presenting here is how we can use high-level language plus the LMS to implement our desired generated code. So we're not like strictly, I mean, the push-based model, the produce-consume, it lends itself to better specialization. But we offer a way to do specialization, but we're not just introducing an evaluation way of doing things. We generate code.
Yeah, no, I understand.
Yeah.
But it's just like some pieces of code are hard to generate once you have basically chosen an abstraction on top of it. I'm wondering where the limitations of your abstraction are.
Well, I have to think about it, not on the top of my head.
Okay.
Yeah, okay.
Do we have any other questions? All right, so then thank you so much.
Thank you again, Holger.
All right, so if we have time, just one more question.
Okay.
So since the last paper, some years have passed, so I'm wondering what improvements have you used the original
So there is the VLDB 14, which is my advisor TRC was part of, but the 2016 we are not part of. So I'm not sure which question.
I mean, you basically have the paper with the same title without the revisited.
So it's a different thing. For them, they were introducing a number of compiler passes. We do everything in a single compiler pass. But if you want to ask about what's the difference between VLDB 14 and this paper, which is TRC, is a common between them. So the data structure there used multiple compiler passes. And the 14 used LMS, we use LMS, the 16 used system compiler.
But what changed in LMS since then?
No change in, I mean, at least the functionalities that we're using, it may be a slight change. We needed an operator or something, yeah. Because the 14, it didn't support all of the operators that we needed. And need to give to hand to the,
Okay, thank you.
yeah. I'm getting stares from,
Thanks again. Now, we all know why we're here. Primarily here for the Eddie Pablo show, and so this is it.
side effects.
Well, okay.